For over 300 years, farmers have been secretly shocking the dirt with electricity to make crops grow larger. And today, this centuries-old obsession has just exploded into a massive viral internet trend with literally millions and millions of followers.
Yeah, I mean, you practically cannot look at a gardening forum right now without seeing it totally dominating the conversation.
Right, so if you've scrolled through social media lately, especially, TikTok or YouTube,
Mm-hmm.
you have probably seen people shoving these bare copper-wrapped sticks into their tomato plants.
Mm-hmm.
And they're claiming it is this ancient suppressed miracle cure for gardening. They call it electroculture. And the claims are completely wild, like zero fertilizer needed, massive yields, total pest immunity.
It's a lot.
So we were taking a massive stack of literature today to really unpack the reality here. We have records from the 18th century French Academy of Sciences. We've got viral digital trends and cutting-edge peer-reviewed research from Linköping University on something called e-soil.
Yeah, plus the latest biophysics data on what they call plasma agriculture.
Exactly. So the mission for this deep dive is to basically separate the genuine, scientifically verified bioelectronic innovation from, the unproven internet hype.
And to pull that off, we have to look really closely at the biophysics of how plant roots transport ions. We're going to uncover the hidden electrical language of vegetation, and we'll look at why electroagronomy is currently caught in this fierce battle between rigorous metrology and, well, just digital folklore.
Yeah, digital folklore is a great way to put it. So to really grasp why this viral craze is happening today, we actually have to rewind all the way back to the Enlightenment.
Right.
Because back then, electricity wasn't just, the utility that powers your refrigerator. It was treated as this invisible, almost magical fluid.
It was a theatrical marvel as much as it was a scientific pursuit. You kind of have to remember the context of the mid-18th century, right?
Yeah.
The tools for storing and measuring electricity were just being invented. So the Leyden jar, which was essentially the very first capacitor capable of storing a static electrical charge, that was developed around 1745. Let's picture what a Leyden jar actually is.
Yeah, paint a picture for us.
It's a glass jar coated inside and out with metal foil, and you have a metal rod going through a stopper connecting to the inner foil.
Right.
When you apply a static charge, usually generated by someone, like furiously cranking a glass friction machine, the glass acts as an insulator. This allows a massive imbalance of electrons to build up between the inner and outer foil.
So they basically built an early battery.
Sort of, yeah.
Yeah.
And suddenly, people held trapped electricity in their hands. And they immediately started wondering what this invisible force could do to living things.
Which leads to one of those absurd historical anecdotes I ever read. So the year 1746, there is this French clergyman and physicist named Jean-Antoine Nollet.
Oh, yeah, Nollet.
And he wants to demonstrate the speed of this new electric fluid. How do you think he does it? He gathers a chain of Carthusian monks. Literally, a huge line of monks holding hands in a circle.
Which is just a crazy visual.
Right. And he discharges a Leyden jar through them just to watch them all physically jump in the air at the exact same fraction of a second.
I mean, it sounds like a parlor trick, but Nollet was a serious experimental physicist. He actually discovered the process of osmosis in natural membranes.
Wait, really? The monk guy discovered osmosis?
Yeah. And crucially, for our timeline of electroagriculture, he started looking at vegetation. Nollet demonstrated to the French Academy of Sciences that when he took seeds in clay pots and electrified them using the sparks from his Leyden jars, those seeds germinated faster. The plants appeared to grow with just greater vigor than the non-electrified control groups. This was arguably the very first systematic comparative protocol where electricity was applied to agriculture.
And he wasn't working in a vacuum either. Because around that same time in the 1740s, a researcher named Stephen de Mainbray started electrifying myrtle trees.
Right.
And he noticed they started budding prematurely, even though it was like the middle of winter in Edinburgh. Other researchers were doing the exact same thing with hyacinth and daffodil bulbs. So the sudden realization swept through the scientific community that electricity fundamentally alters plant biology.
Exactly. And those empirical observations began snowballing into dedicated agricultural theories by the 1780s, which brings us to Pierre-Nicolas Berthelon. In 1783, he published a massive 400-page treatise summarizing decades of field experiments.
Wow, 400 pages just on shocking plants.
Yeah, but Berthelon went way beyond writing. He invented a physical device called the electrovegetometer.
Okay, I am fascinated by the electrovegetometer Because based on the descriptions, this wasn't just some subtle little wire. It was this towering, intimidating copper antenna designed to literally catch naturally occurring atmospheric electricity from the sky and just aggressively channel it down into crop beds.
The ambition was staggering. I mean, Berthelon's operating principle was to embed the action of electricity into everyday irrigation and farming routines.
Yeah.
He genuinely believed that if you could capture the static electricity floating in the air and direct it into the soil, you could beneficially modulate plant functions. And this concept kept evolving well into the late 19th century.
Right, because then we see researchers like the Finnish physicist Carl Lemstrom taking this to extreme environments.
Yeah.
In 1868, Lemstrom was on an expedition in high latitudes and noticed a really strong correlation between the rapid, lush growth of vegetation and the intense electrical activity of the aurora borealis.
Yeah, he looked up at the northern lights and hypothesized that the massive electric fields in the sky were actively reaching down and fertilizing the pine trees.
Which is such a poetic idea.
It is. And he was convinced the atmospheric electric field was the missing variable, so he spent 15 years conducting research in Lapland and Bavaria to prove it. But Lemstrom didn't just stick a rod in the ground.
No, he went way bigger.
He suspended massive overhead high-voltage wire grids about 2 to 4 meters high directly above agricultural fields to apply continuous static charges to the crops below. And his published data documented yield increases of 30 to 45% in crops like barley and potatoes.
A 45% increase is just a paradigm-shifting number for a farmer. And the momentum didn't stop with Lemstrom, right? Fast forward to 1926, and the French Ministry of Agriculture actually steps in. They conducted official trials across 47 different farms in places like Brittany to test a system designed by a man named Justin Christofleau. He used these elaborate copper-zinc antennas, claiming to harvest both atmospheric currents from the air and telluric currents, meaning naturally occurring electrical currents flowing through the Earth's crust.
Like Earth batteries.
Exactly. And the results they documented were astonishing. They recorded average wheat yields of 7.4 tons per hectare in the electrified plots, compared to a regional average of just 3.6 tons. They essentially doubled the yield of an entire farm using metal poles.
On paper, those numbers are earth-shattering. But looking back with modern scientific rigor, a massive flaw emerges in their methodology. The results seem like definitive proof, but they completely lacked modern metrology.
Let's define metrology for a second. We're basically talking about the fundamental science of measurement, right?
Yeah, the ability to measure the cause and the effect precisely. When we analyze Berthelon, Lemstrom, and Christofleau, their early electroculture experiments relied on zero quantitative dosimetry.
Dosimetry being?
Dosimetry is the exact measurement of the energy actually being absorbed by the biological target. They had no way to measure exact voltages at the micro level of the root zone. They certainly weren't measuring chemical byproducts in the soil.
So they were just flying blind.
Totally blind. The devices of the time could only give coarse qualitative indicators. You could count how many times a spark jumped across a gap, but you couldn't quantify the flux of the charge entering the cellular walls of a potato.
It makes me think of, like, trying to water a delicate single house plant using a high-pressure fire hose.
Oh, that's a good comparison.
You know the plant needs water to survive, and you know the fire hose has water in it, but you have absolutely zero control over the flow rate, the pressure, or the volume. So you turn it on, and you end up just blasting all the dirt out of the pot. They knew the energy was there, but they had absolutely no precision instrument to tune it.
The fire hose analogy captures the mechanical failure perfectly. It was a conceptually visionary era, but it was technologically premature. The massive yields they reported were highly dependent on uncontrolled variables.
Like the weather.
Weather conditions, soil heterogeneity, localized rainfall, seasonal effects. If you put a giant metal antenna in a field, you might just be changing the way condensation drips onto the soil, altering the localized hydration.
Oh, I hadn't even thought of that.
Yeah, or the metal itself might be slowly corroding and leaching trace minerals into the dirt. They saw a positive result, and they attributed it entirely to the magical electrical fluid, but they just didn't have the statistical tools to isolate those variables.
Which explains why the practice basically vanished. In the mid-20th century, cheap synthetic chemical fertilizers hit the market. Nitrogen, phosphorus, and potassium, the NPK fertilizers.
The Green Revolution, yeah.
Suddenly, a farmer didn't have to build a giant copper grid and pray for a thunderstorm. They could just buy a bag of nitrate, dump it on the field, and guarantee a standardized, predictable yield. The certainty of chemical analysis just totally replaced the erratic nature of the electrical research.
History, however, has a habit of circling back. Because now, 100 years later, the global agricultural community is waking up to the severe ecological damage of those synthetic chemicals.
Right.
We are dealing with massive nitrogen runoff, creating dead zones in the oceans, severe soil depletion, and a massive carbon footprint from manufacturing the fertilizer. That intense desire for clean, sustainable agriculture has resurrected electroculture from the grave. But it has come back in a highly distorted way.
Which brings us to the modern era. If you go on TikTok right now, the hashtag Electroculture has nearly 100 million views. There are massive Facebook groups boasting hundreds of thousands of members. But what they are promoting relies heavily on what is called passive electroculture.
And the distinction between passive and active is the critical fault line between the digital folklore and the actual biophysics.
Right. So when we say passive, we mean they aren't using power supplies or solar panels or batteries. They are taking unpowered, bare, copper-wrapped dowels, shaping them into Fibonacci spirals or geometric rings, and just shoving them into the potting soil next to a houseplant.
Exactly.
The core claim is that these specific geometric shapes act as antennas to harvest atmospheric or cosmotelluric energy, dragging it from the ether down to supercharge the roots. You see these videos of people standing next to towering 8-foot-tall tomato plants swearing it's entirely because of a piece of copper wire twisted around a wooden stake.
The modern trend is fascinating purely from a sociological perspective, because of how it co-opts the language of genuine physics. The proponents use terms like electromagnetic frequencies, resonance, and cosmic energy.
Which sounds incredibly scientific to a layperson.
It does, but when you consult the peer-reviewed agricultural literature, the rigorous counter-evidence against passive antennas is overwhelming. Peer-reviewed research validating these strictly passive, unpowered techniques essentially vanished after 1968. The modern scientific community widely classifies passive electroculture as pseudoscience.
Okay, let's look at the hard data disproving the passive antennas. There is a landmark study from the University of Copenhagen that ran from 2018 to 2020. They tested copper antenna arrays across 12 different tomato plots over 3 full growing seasons. And they didn't just eyeball the plants, they tested the Brix score.
And the Brix score is a vital metric here. It's a measurement of the dissolved solids in a liquid, primarily sucrose. In agriculture, it's the gold standard for measuring fruit quality and metabolic success. A higher Brix means a sweeter, more nutrient-dense tomato. 1 degree Brix equals 1 gram of sucrose in 100 grams of solution.
So they're looking to see if the cosmic energy captured by the copper makes the tomato demonstrably sweeter or heavier. What do they find? 0 statistically significant improvements in fruit weight, 0 difference in the Brix score, 0 difference in the days it took to first flower, and 0 difference in the foliar chlorophyll content compared to the control groups.
Yeah, and a parallel study out of Marquette University investigated the exact same claims. They tested the passive copper setups on urban container gardens growing mustard greens, kale, beets, and turnips. They specifically measured stomatal conductance and net assimilation.
Stomatal conductance basically refers to how well the plant is breathing.
Precisely. Plants have tiny pores on their leaves called stomata. Stomatal conductance measures the rate of carbon dioxide entering or water vapor exiting through those pores.
So it's like measuring the RPM of a car engine.
Right. It is a direct indicator of the plant's photosynthetic engine. If a plant is truly supercharged by energy, the stomatal conductance will spike because it is processing CO2 at a faster rate. The Marquette study found the passive copper rods did absolutely nothing to alter stomatal conductance or net assimilation.
Nothing at all.
Nothing. And if we look at the fundamental physics of electricity, the math explains exactly why passive copper rods fail to do anything.
Okay, let's break down the math. Because if I'm looking at a piece of copper wire, my instinct is, copper conducts electricity in my house, so it must be conducting something into the dirt.
Copper is an excellent conductor, yes, but conductivity is meaningless without a voltage differential to drive the current. To transmit any significant electrical energy into the soil, you need a substantial difference in electrical potential between the top of the antenna and the ground. Now, there is a natural voltage gradient in the Earth's atmosphere. The Earth functions somewhat like a giant spherical capacitor. The surface is negatively charged, and the upper atmosphere, the ionosphere, is positively charged. This creates an atmospheric voltage gradient of roughly 100 volts per meter of elevation near the ground.
Wait, 100 volts per meter. That sounds like a massive amount of electricity just floating in the air.
It sounds massive, but we have to apply it to the geometry of a typical garden setup. If you put a 40-centimeter copper rod into your raised garden bed, the voltage differential between the top of that rod and the surface of the soil is only about 4 volts.
Oh.
That is a minuscule differential. But more importantly, the air itself is an incredible insulator. The flow of electrons driven by that 4-volt differential through the high resistance of the air and the soil is measured in picoamperes.
What's a picoampere?
A picofarad is 1/trillionth of an ampere.
Okay, so essentially nothing.
It is orders of magnitude too low to trigger any physiological or chemical response in a plant cell. Furthermore, many of these DIY internet setups encourage using dissimilar metals. You'll see tutorials telling people to wrap copper wire around a galvanized zinc nail and bury the whole thing in moist soil.
Ah, yeah, I've seen that. The videos usually call that an earth battery. They stick the metal in the dirt, hook up a multimeter, and show the camera that the dirt is magically producing a volt of electricity.
They are producing a volt of electricity, but it has absolutely nothing to do with cosmic energy. When you place two dissimilar metals, like copper and zinc, into an electrolyte, and moist, slightly acidic potting soil is a perfect electrolyte, you create a weak galvanic cell.
So it literally is just a battery.
It is basic battery chemistry. Zinc is the more reactive metal, so it acts as the anode. It gives up electrons and begins to slowly corrode and dissolve. The copper acts as the cathode. You generate roughly 0.8 to 1.1 volts this way. It is just enough to make the digital display on a multimeter flicker, which makes for very convincing video content.
But what is actually happening beneath the soil surface while that multimeter is flickering?
What is happening chemically is highly problematic for the plant. That galvanic reaction is actively leaching heavy metal ions, specifically copper 2+ and zinc 2+ ions, directly into the dirt surrounding the roots.
Well.
And at elevated concentrations, these heavy metals are highly phytotoxic. A 2021 study published in the journal Plant and Soil documented this exact scenario. They placed copper-zinc electrode pairs in the soil and measured the localized impact. They recorded a 37% reduction in radish root biomass compared to the control groups.
37% reduction.
Yeah, the heavy metal ions essentially disrupted the root cell membranes and poisoned the localized root zone.
Wait, hold on. Let me just channel the skepticism of someone listening to this right now. If I go on YouTube, I can see a guy standing next to a cabbage the size of a car tire. And he's holding his copper spiral, swearing it worked. Are you telling me that's 100% fake? Because the video evidence looks incredibly convincing. If the copper doesn't work, how did the cabbage get that big?
It is a totally valid question, and the answer comes down to human psychology and horticultural confounders. It is not necessarily that the gardener is lying to the camera, it's that they are misattributing the cause of this success. In agriculture, we often look at the 70-30 rule of intervention.
What's the 70-30 rule?
When a gardener decides to try a new hack like building a Fibonacci copper antenna, they suddenly become hyper-invested in the success of that specific garden bed.
Oh, so they start babying the plant.
Exactly. Without even realizing it, they start paying much closer attention to watering schedules. They pull weeds faster. They monitor for aphids more aggressively. They ensure the soil aeration is perfect. That massive increase in observational care and basic husbandry is what ultimately boosts the yield.
That makes so much sense.
Furthermore, there is a chemical confounder. Copper is actually an essential trace micronutrient for plants. It is required for lignin synthesis in certain enzymatic reactions. If a gardener happens to be planting in soil that is severely depleted of trace minerals, a slowly corroding copper wire might act as a very slow-release micronutrient supplement.
So the plant experiences a growth spurt because it is chemically metabolizing the copper nutrient, not because the wire is acting as an electrical catalyst harvesting cosmic waves.
Exactly.
So to summarize the passive trend, buying expensive copper wire at the hardware store to build atmospheric antennas is basically a potentially toxic placebo for your garden.
The scientific consensus is definitive. The atmospheric voltages captured by a tiny rod are too low to matter. There is no validated biological mechanism for passive atmospheric energy harvesting, and the heavy metal leaching from dissimilar metals is a verified risk to the soil biome.
Okay, so it's sticking unpowered metal in the mud is a dead end. Does that mean electricity has absolutely no place in agriculture? Because that leads us into the genuine biophysics, the actual verified reality that plants are, in fact, bioelectric networks.
This is where the science pivots from folklore to something truly incredible. The underlying biophysical principle that plants are electrically active organisms responsive to physical stimuli is an absolute reality. Electricity does affect plants, it just requires active, controlled, and mathematically precise electrical applications.
Let's break down this idea of a bioelectric network, because I think most people look at a fern or stalk of corn and just see a static, inanimate object. It drinks water, it absorbs sunlight, it grows. But the literature reveals they are actually humming with electricity.
They are highly sophisticated electrical systems. Plants obviously do not have a central nervous system or a brain like mammals do, but they generate internal electric fields through the movement of ions across their cellular membranes. They use what are called action potentials.
Like human nerves.
Exactly. An action potential is a rapid, transient spike in cellular voltage. It is the exact same fundamental mechanism that a human nerve cell uses to send a signal to a muscle.
So if a plant experiences trauma, say a caterpillar takes a bite out of a leaf,
The moment that mechanical wounding occurs, the cells at the site of the bite experience a sudden influx of calcium ions. This triggers a massive depolarization of the cell membrane, firing an action potential.
wow,
And that electrical signal propagates rapidly through the plant's vascular system, traveling down the phloem from the wounded leaf all the way to the root tips in a matter of seconds.
that is just wild to me.
The plant uses this electrical signal to communicate systemically. It can trigger defensive biochemical cascades in leaves on the other side of the plant, telling them to produce bitter-tasting alkaloids to deter the caterpillar. It can also adjust that stomatal conductance we talked about earlier, closing its pores to prevent water loss during a stress event. The roots themselves actively release charged compounds into the soil to modulate local electric fields and enhance nutrient uptake.
So they have their own internal high-speed internet. So knowing that the plant operates on this electrical currency, what happens when human beings intervene and introduce an active, controlled, low-voltage current to this system?
Decades of plant physiology research have documented a phenomenon called electrotropism. In controlled laboratory settings, if you expose plant roots to even tiny active voltage gradients, some studies demonstrate sensitivity to fields as weak as 1 millivolt per centimeter, the roots will physically alter their growth trajectory.
Wait, they move toward the electricity.
They will bend and grow purposefully toward the cathode, the negative electrode. The applied current profoundly alters the electrochemical potential across the plant's cell membranes.
And it goes beyond just making the roots bend in a certain direction, right? It fundamentally changes how the plant feeds. Let's dig into a specific example. There's a fascinating study from Normal University that perfectly demonstrates the power of active electrical stimulation.
Yeah, the team at Normal University, led by Zhongguang Li, constructed an elegant experiment using maize seeds, so corn. They took the seeds and applied an active 22-volt stimulus, but they didn't leave it on forever. They applied the current for exactly 10 minutes.
That's 10 minutes.
A single 10-minute controlled exposure before germination. And the results were dramatic. That brief electrical pulse significantly boosted the subsequent germination rates. It increased shoot length, enhanced root development, and increased overall seedling fresh weight compared to the unshocked controls.
That's incredible.
It also dramatically improved their thermotolerance, giving the plants a massive resistance to extreme heat stress later in their life cycle.
But how? Like, what is the actual mechanical event happening inside the microscopic cellular structure of that seed during those 10 minutes that causes it to grow so fast?
It all comes down to the physical mechanics of ion transport and enzyme activation. Surrounding every plant cell is a lipid bilayer, a membrane that acts as a secure border wall. Embedded in that wall are specialized proteins called voltage-gated ion channels.
Okay, I'm following.
Normally, these channels open and close based on the plant's internal signaling. But when the researchers applied the 22-volt electrical current, the external electric field physically contorted the shape of those protein channels, forcing them open.
It pried the doors open.
Exactly. And by forcing those channels open, the electrical field significantly enhanced the mobility of charged essential nutrients, specifically potassium, calcium, and magnesium ions. It forced these minerals across the cellular barriers much faster and in higher volumes than passive diffusion would allow.
Yeah.
Furthermore, the electrical stimulus triggered something called ROS signaling.
Let's define ROS real quick.
Yeah.
Reactive oxygen species.
Right. Reactive oxygen species are highly reactive chemical molecules containing oxygen, like hydrogen peroxide or superoxide. In high amounts, they cause oxidative stress and damage cells. but in small, controlled bursts, like the burst created by the 22-volt shock ROS, act as vital chemical messengers.
So it's like a biological alarm bell.
Yes. The sudden spike in ROS signals the plant's DNA to upregulate the production of key antioxidant enzymes like peroxidase and catalase. This biological panic response accelerates the mobilization of reserve starches and proteins stored inside the seed, essentially kickstarting the seed's metabolism into overdrive.
I want to try an analogy here to make sure this is perfectly clear. It's kind of like the plant has a highway for nutrients. Normally, minerals are stuck in a massive traffic jam at the cell wall toll booth, just waiting to get processed and allowed inside.
Good analogy, yeah.
But the active electrical current acts like a rogue toll booth operator. It physically grabs the cars, the potassium calcium ions, and just hurls them onto the highway. It opens up an easy pass VIP lane, forcing the nutrients right into the root, so the plant has an overabundance of building materials instantly.
The toll booth analogy is incredibly precise regarding the ion channels. But the active current doesn't just manipulate the internal biology of the plant, it also profoundly influences the external environment, specifically the rhizosphere.
The rhizosphere. That is the immediate microscopic zone of soil directly surrounding the plant roots.
Right. And the rhizosphere is arguably the most complex ecosystem on Earth. It is teeming with microbial life bacteria and fungi that live in a symbiotic relationship with the plant. Applying a weak electrical current to the growth substrate actively energizes that soil microbiome.
How so?
The current acts as an electron donor, accelerating bacterial and fungal metabolism and reproduction. These hyper-energized microbes begin breaking down organic matter in the soil much faster, which improves soil aeration and increases the bioavailability of nutrients, particularly nitrogen.
Oh, so the soil itself becomes better.
Yes, and additionally, as the current passes through the moisture in the soil, it causes localized electrolysis. It literally splits the water molecules, generating extra dissolved oxygen at the soil-water boundary. This oxygenation supports intense root respiration and fights off anaerobic root pathogens that cause rot.
Okay, so applying active electricity works. It opens the biological toll booths and supercharges the microbial life in the soil. But, this creates a massive logistical problem. A farmer can't just hook up a 22-volt car battery to 10,000 acres of cornfield. And we already established that if you use bare metal electrodes, the electricity will cause the metal to degrade and leach toxic zinc or copper directly into the food supply.
Right.
So how does modern science actually deliver this current safely? Did anyone figure out a way to replace the toxic metal entirely?
They did. And it brings us to what is arguably the most exciting breakthrough in modern bioelectronic agronomy: e-soil.
E-soil. It sounds like something straight out of a science fiction novel. The research on this was published across 2023 and 2024 by Eleni Stavrinidou and her ePlants team at Linköping University's Laboratory of Organic Electronics in Sweden. They literally invented an electronic dirt.
It is a staggering piece of material engineering. To be highly specific, e-soil is a 3D, porous, conductive, completely biodegradable growth scaffold designed specifically for hydroponic cultivation.
Let's contextualize hydroponics for a second. Hydroponics is growing plants without traditional dirt, usually indoors in controlled vertical farms, using nutrient-rich water. It is seen as the future of agriculture because it uses a fraction of the water of traditional farming. But right now, most commercial hydroponic farms have to anchor the plant roots in something called rock wool.
Rock wool, or mineral wool, is the industry standard. It is manufactured by taking basaltic rock and chalk, heating them to nearly 3,000 degrees Fahrenheit until they melt into lava, and then spinning that lava into fine fibers.
Sounds incredibly energy intensive.
It is. It provides excellent structural support for the roots, but the manufacturing process has a massive carbon footprint. More importantly, rock wool is completely non-biodegradable. When a commercial farm is done with a crop cycle, the rock wool just gets thrown away and sits in a landfill indefinitely.
Right.
The Linköping team wanted to replace rock wool with a sustainable, biodegradable alternative, and they wanted to integrate active electrical stimulation at the exact same time without using heavy metals.
So what is e-soil actually made of? How do you make dirt conduct electricity without metal?
The structural matrix of e-soil consists of nanofibrillated cellulose. Cellulose is derived from wood pulp. It is the structural component of the primary cell wall of green plants, making it the most abundant biopolymer on Earth. They took this organic cellulose and mixed it with a highly specialized conductive polymer called PDOT.PSS.
Scientists love a catchy acronym. What does PDOT.PSS stand for, and why is it the secret ingredient here?
It stands for poly 3-4-ethylene deoxythiophene. polystyrene sulfonate.
Yeah, we will definitely stick with pitot.
Good call. Pitot is revolutionary because it is an organic mixed ionic electronic conductor, or OMIEC. Most polymers, like the plastics we use every day, are insulators. They block electricity. Pitot is unique because it is stable in wet, aqueous environments, like a hydroponic water system, and it has the rare ability to conduct both ions and electrons.
Why does that matter?
Biological systems use ions to communicate. Electronic systems use electrons. Pitot acts as a translator between the two. Because it is thoroughly mixed into the porous cellulose sponge, the entire scaffold becomes an active, stimulating electrode. There are no wires poking the plant. The root system grows naturally into the matrix, meaning the delicate root hairs are entirely bathed in the electric field.
So they have this conductive, biodegradable, organic sponge. Let's look at the actual experiment they ran. They used barley seedlings. Barley is a massive global crop, widely used for animal fodder and brewing. They planted the barley in the e-soil, and they applied a tiny constant voltage, just plus 0.5 volts, half a single volt, and they only ran the current for exactly 5 days.
And the outcome was phenomenal. They compared the electrically stimulated barley seedlings to a control group grown in identical e-soil that received no electricity. The stimulated seedlings saw their dry weight biomass increase by a massive 50% over a 15-day growth period.
A 50% increase in total mass in 2 weeks, just from a half-volt whisper of electricity applied to a wood pulp sponge.
Yeah, and they also recorded an overall increase in plant length of over 31%.
But the timeline of the growth is the most crucial detail here. The researchers tracked the growth day by day, and the massive growth explosion didn't actually happen during the 5 days the electricity was turned on.
That delayed response is perhaps the most fascinating finding of the entire study because it proves the mechanism. They harvested and weighed plants at day 5, day 10, which was the exact end of the 5-day electrical stimulation, and day 15. At day 10, the dry weight of the stimulated plants and the control plants was virtually identical.
Wow, okay.
The accelerated 50% growth happened entirely in the following 5 days, long after the electricity had been turned off.
Why does that delay matter so much? Does it mean the electricity fundamentally reprogrammed the plant rather than just acting as a temporary steroid?
Exactly. It signifies developmental reprogramming. If the electricity was just forcefully shoving nutrients into the root, the plant would only grow faster while the power was on. The fact that the growth happened days later proves that the brief electrical stimulus triggered a lasting physiological change in how the plant metabolizes its food.
That is amazing.
And the Linköping team used incredibly sophisticated chemistry to figure out exactly how the metabolism changed. They discovered that the electrically stimulated seedlings were reducing and assimilating nitrate NO3 minus far more efficiently than the control group.
Let's stop and talk about nitrate assimilation. Why is making a plant better at processing nitrogen the holy grail of agricultural science?
Because nitrogen availability is the single most limiting factor for plant growth on planet Earth. It is the core building block of amino acids, proteins, and chlorophyll. It's why humanity invented the Haber-Bosch process to synthetically pull nitrogen from the air and manufacture the millions of tons of chemical fertilizer we dump onto global crop fields every year.
Right.
Much of that fertilizer washes away into rivers, causing eutrophication toxic algae blooms that suffocate marine life. In the e-soil experiment, the researchers used a nitrogen-15 isotope tracer to track exactly what the plants were doing.
How does an isotope tracer work in this context?
If you just look at a plant and see it grew larger, you don't actually know how it used the nutrients in the water. So the researchers swapped out regular nitrogen-14 in the fertilizer for its heavier cousin, nitrogen-15. Nitrogen-15 has an extra neutron in its nucleus.
Okay.
The plant doesn't know the difference. It absorbs the heavy nitrogen the same way. But later, scientists can harvest the plant tissue and run it through a mass spectrometer. Because nitrogen-15 is physically heavier, the machine can separate it out and tell the researchers exactly how much of that specific nitrogen made it into the cellular walls of the barley.
That's incredibly clever.
It is. And they found that the stimulated plants didn't necessarily absorb a greater volume of nitrogen from the water, but they were significantly more efficient at metabolizing and converting the nitrate they did absorb into structural biomass.
Going back to our toll booth analogy, it's not just that the toll booth is throwing more cars onto the highway. It's like the cars, the nutrients getting off the highway, are suddenly transformed into highly efficient hybrid vehicles. The plant is doing 50% more physical growing using the exact same amount of fuel.
Yes.
And they achieved this metabolic upgrade without changing the pH of the water, without changing the temperature and without altering the dissolved oxygen levels. It was pure bioelectronic efficiency.
The global implications of this are staggering. If we can make plant hyper-efficient at processing nitrogen, we could drastically cut down on global chemical fertilizer use without sacrificing yield. Furthermore, this e-soil technology consumes almost zero power. We're talking about microwatts.
Wow.
Yeah, an entire commercial greenhouse could be powered by a single, small solar panel. It's completely biodegradable, meaning you can compost the e-soil after the harvest. It has the potential to revolutionize closed environment agriculture, vertical farming, and hydroponic food production, especially in regions with poor soil quality, severe water restrictions, or limited arable land.
I am totally blown away by the elegance of e-soil. It solves the heavy metal toxicity problem perfectly. But I have to look at the reality of global farming. This sounds incredible for a high-tech indoor vertical farm growing hydroponic lettuce in a warehouse. But what does this mean for a massive 10,000-acre wheat farm in the American Midwest?
Right, the scalability issue.
Yeah, you cannot exactly bury millions of conductive cellulose sponges across thousands of acres and wire them all up to solar panels. Is this bioelectronic revolution strictly confined to the indoors?
That is a very astute observation of the physical limits of the technology. E-soil is indeed a masterclass solution for controlled indoor environments. Scaling physical, wired scaffolds to broadacre, traditional soil farming is currently logistically and economically impractical.
Okay.
However, that does not mean electroagronomy is limited to the indoors. Scientists are taking the fundamental electrical concepts we just discussed and applying them to broad-scale agriculture in a futuristic way that doesn't require a single wire in the dirt.
Which brings us to the final frontier of our deep dive, plasma agriculture. When I hear the word plasma, my mind immediately goes to blood plasma in a hospital or maybe a plasma screen TV or, the surface of the sun. What exactly is plasma in an agricultural context?
We're talking about the fourth fundamental state of matter. You have solid, liquid, gas, and then if you add enough energy to a gas, the atoms begin to break apart. It ionizes.
Okay.
The electrons are stripped from the nuclei, creating a soup of freely moving electrons and ions. That energetic soup is plasma. Specifically in agriculture, we're talking about cold atmospheric plasma, or CAP.
Cold plasma. That seems like an oxymoron. If it's pure energetic ionization, shouldn't it be incredibly hot? Obviously, we can't blast delicate seeds with the heat of the sun.
It is cold because of how it is generated. Scientists use specialized equipment like a dielectric barrier discharge reactor. They apply a high-voltage alternating current across a gap filled with a gas, like ambient air or argon, but they limit the current so only the tiny electrons get hot, while the heavier gas molecules remain near room temperature.
Oh, that makes sense.
You get the reactive chemistry of a plasma without the destructive thermal heat. And unlike the 18th century electrovegetometer, where Abbé Berthelon blindly hoped to catch a random atmospheric spark, modern plasma agriculture relies on strict, highly traceable dosimetry.
There's that word again, dosimetry, the precision of the ghosts.
Yes. In plasma agriculture, they measure explicit physical metrics. They calculate the UV fluence, the exact electrical energy dose in joules per square centimeter, and the precise parts per million concentration of chemical species generated. Because when you generate cold atmospheric plasma in the air, you are simultaneously co-generating several physical phenomena.
Like what?
You create localized electric fields, you emit mild ultraviolet radiation, and crucially, the energetic electrons smash into the nitrogen and oxygen in the air, creating what are known as Raw-ness reactive oxygen and nitrogen species.
Okay, so we have this cold, glowing soup of reactive chemicals and electric fields. How does a farmer actually apply this to a 10,000-acre wheat farm?
The most viable broad-scale application is direct seed treatment. Before a farmer ever puts a seed in the ground, they can run massive batches of dry seeds through a cold plasma exposure chamber on a conveyor belt. The cold plasma physically modifies the microscopic surface of the seed.
Interesting.
The bombardment of ions causes microetching on the tough outer seed coat. This etching fundamentally changes the seed's hydrophilicity.
Hydrophilicity meaning how much it loves water.
Exactly. The etched seed coat can suddenly absorb water much faster and much more uniformly than a normal seed. This accelerates imbibition water uptake and drastically speeds up germination kinetics.
Wow.
Simultaneously, the UV radiation and the highly reactive RONs from the plasma gently disinfect the seed surface. They shred the cellular walls of bacteria and fungal spores, drastically reducing the microbial load of pathogens before the seed is even planted.
Wait, I just realized something incredible. We are essentially manufacturing highly engineered micro-thunderstorms in a laboratory to give seeds a superpower shield and a hypermetabolism before they are planted. And if we look back at the history,
Yes, the historical loop closes perfectly right here.
think back to Carl Lemstrom and the early 18th century scientists. They noticed that crops always grew dramatically better and greener immediately after a severe thunderstorm. They thought it was the raw static electricity from the lightning shocking the roots. But modern science showed us that lightning is actually a giant, naturally occurring plasma discharge.
Exactly.
When lightning flashes through the sky, the immense energy breaks apart the triple bonds of atmospheric nitrogen gas. The nitrogen bonds with oxygen to create nitrogen oxides, which dissolve in the falling rain to form nitrates. The lightning literally manufactures liquid nitrogen fertilizer out of thin air, and it falls on the crops.
The early pioneers observed a very real, very powerful natural phenomenon. They just completely misunderstood the mechanical causality. It wasn't the electricity directly shocking the roots in the mud. The electricity was manufacturing plasma, and the plasma was manufacturing fertilizer in the rain.
That is brilliant.
Today, scientists use cold plasma to artificially create this lightning in a bottle. They can literally bubble cold plasma through standard irrigation water to create plasma-activated water, or PAW. This PAW is loaded with those trace nitrates and hydrogen peroxide. When a farmer sprays it onto crops, it triggers redox priming.
Redox priming.
Yeah. The plant senses the mild reactive species and activates its antioxidant and defense pathways, significantly improving its tolerance to drought and disease without relying on heavy, toxic chemical pesticides.
And the applications don't stop at the field level, do they? The literature mentions agri-food sanitation as well.
The same plasma technology is being deployed post-harvest. Engineers are developing in-package plasma. Imagine fresh spinach sealed in a plastic container. A brief high-voltage pulse creates a cold plasma inside the sealed headspace of the package.
So it cleans it while it's in the box.
Yes. The reactive species sanitize the surface of the spinach leaves, killing E. coli and salmonella, and drastically extending the shelf life without using thermal heat that would wilt the produce. Plasma jets are also being used to blast away stubborn bacterial biofilms on food contact equipment in massive processing plants. It is a comprehensive, physics-based approach to securing the entire agricultural supply chain.
We have covered an immense amount of ground today, from French monks jumping in a circle in the 1700s, to viral TikTok copper wires, to biodegradable electronic dirt, and finally to capturing lightning in a bottle with plasma. Let's synthesize all of this information for the listener into a clear, honest, and balanced takeaway. When someone asks about electroculture, what is the final verdict?
The verdict requires distinguishing the medium from the mechanism. The current viral internet trend of shoving passive, unpowered copper wires and metal spirals into garden soil is scientifically unfounded hype. Passive rods do not generate the required voltage differential to influence plant physiology, and they carry a verified risk of leaching phytotoxic heavy metals into your home garden. It is, unfortunately, a waste of time and money, driven largely by confirmation bias and the 70-30 rule of increased gardening attention.
So if you are listening to this, save your money. Skip the expensive copper antennas at the hardware store.
However, the underlying principle, the core idea that plants are dynamic, bioelectrical networks that respond profoundly to active, precise electrical and plasma stimulation, is an absolute, verified reality. It is not pseudoscience. Genuine scientific innovations, like the low-voltage active e-soil scaffolds from Linköping University and the highly precise dosimetry of cold atmospheric plasma treatments, are producing real, reproducible, paradigm-shifting results.
Right.
They are enhancing nitrate assimilation by 50%, boosting germination, and offering a tangible path to massively reducing our reliance on synthetic chemical fertilizers. That is where the real future of sustainable agriculture lies.
The history was right to look for the spark. But it took modern biophysics to finally build the engine to harness it safely, which is just an incredible thought. I want to encourage you, the listener, to walk outside and look the plants in your home or your garden a little differently today. Don't just look at a fern or a tree as a static green decoration. Try to see them as dynamic, electrically humming networks, firing off invisible action potentials, constantly chatting with the soil microbiome in a high-speed language of ions and voltages.
Once you understand the biophysics, it completely changes your perspective on the complexity of biology.
It really does.
Yeah.
And I want to leave you with one final mind-bending concept to ponder on your own. We spent this whole deep dive talking about the history of human beings trying to send electricity into the plants, to bend them to our will, to make them grow faster, to yield more food. But what if, knowing that plants are this incredibly sensitive to ambient electrical fields and microscopic ionic shifts, we could one day reverse the interface?
Using the plant's internal network as an output instead of an input.
Exactly.
Mhm.
Instead of sending electricity in, what if we tapped into their internal electrical networks to listen? Imagine a future where we use entire old-growth forests as giant, living environmental sensors. We could harmlessly plug into a tree's action potentials, let the tree send us an electronic alert the moment a localized drought begins deep in the soil, or the second a microscopic invasive pest arrives, long before a single leaf turns brown or a human satellite detects a problem. From farmers secretly shocking the dirt 300 years ago hoping for a bigger potato, to letting the dirt literally shock us with real-time ecological data. Now, that is a truly electrifying thought.
A fascinating prospect for the future of bioelectronics.
Thanks for joining us on this journey. Keep questioning, keep learning, and we'll see you on the next deep dive.